So here we are. This is the moment everything with the limit has been building up to, and that is the derivative. And I'm going to make this as large as I can fit in there because that's how important the derivative is. And the derivative will actually be the subject of test 2 and test 3. So we will talk a lot more about the derivative. And I want to begin by setting the stage here for what the derivative is, and then how we're going to get it in this last section here before the test. So I just want to reiterate that again, that we will be talking a lot more about the derivative. So if some things aren't quite sinking in about it, we'll have plenty of more time to talk about it. So let's begin with something that you're already familiar with, and that's a linear function. And a linear function, I'm sure you talked about many times, about its slope. And you got that from rise over run. And so we just made this statement we called the slope m, and we defined it as the rise over the run. Now that's with words. We can't do any math with these words yet. We have to put some variables down here. And so what you probably did is you put an x1 here, x2 here, and then your x1 led to your y output, and your x2 led to your y2 output. And then with this notation here, you can then define the rise to be y2 minus y1, and then the run as x2 minus x1. So hopefully that's something that's familiar from algebra. And we are actually going to use this expression and build from it and see how it gets us to the derivative. So one thing you, I'm sure, never did with this slope function was apply it to something that had curvature. So we're going to do that. We're going to take this function, rise over run, y2 minus y1, x2 minus x1, and we're going to apply it to something that has curvature. And so I'm going to pick my points, x1 and x2, just wherever. Here they are. And of course, we draw our lines then to the output to get our y2 and y1. And what does this mean then? So this slope, y2, y1 minus x2 minus x1, what does that mean? Well, it means it's the slope that connects these 2 points. So if I took these 2 points on a function and connected them with a linear function, then this formula again of y2 minus 1 over x2 minus x1 is giving us the slope of the function, the linear line that connects these 2 points. And in general, we call this blue line the secant line. And what this secant line means is it's the average change from x1 to x2. So if you want to go from this point x1 to this point x2, you could follow the function along, and that'll get you to x2. Or you can find an average change and then just walk a straight line to that point. And now the average does mean here the average slope that we would have of this function. So imagine this, just this top red line here. Imagine we could break this down into a bunch of straight lines. So instead of having a nice curvature there, imagine that we're going to break that into these straight lines to kind of form that pathway. And then each of these lines has a slope to it. And so the secant, the black line here then, is the average of those slopes. It's the average rate of change between the 2 points. It's literally the average of all those slopes. Now, I did draw in finite many slopes here. So I drew in, 1, 2, 3, 4, 5, 6. So I got 6 lines here. What we're going to do, though, is we're going to make this red line become infinitely many straight lines. So we're going to create this curvature with these straight lines, but we're going to draw so many straight lines, infinitely many of them, that it's then going to look curved. And how are we going to do that? Well, we're going to start with our rise over run. And that's the blue line again. In general, this line is called the secant line. And what we're going to do is we're going to take this x2 and move it closer and closer and closer to x1. So we're going to take x2 and move it closer and closer and closer to x1. And notice that the blue line changes a lot immediately, but as we get closer and closer to x1, it hardly is changing at all. And what we're going to do is we're going to let x1 and x2 get infinitesimally close. And we will do that with the limit. So this is the process we're going to do. Is we're going to take a secant line, and then we're going to let x2 get forever closer to x1. And when we do that, we say the secant line is then approaching the tangent line. Now the tangent line is the slope of the function at that point. So right at this point here at x1, that little slice of the function has this slope that is blue. We call that the tangent line. So we have our secant line, which is 2 points are required. And we have our tangent line. The tangent line, we only need 1 point. Let me say that again. Oh, I forgot to also mention the tangent line is also called the instantaneous change at x1. So what we're saying here is that this red line, the original function, is we're going to draw this line as a sum of infinitely many straight lines. And each of those straight lines will have a slope to it. And we're going to find the slope of all of those infinitely many slices. We're going to find the slope everywhere on a function, even if it's curved. So this is how we do that. We'll start with the secant line. And we're going to change notation here. This notation isn't too friendly with where we're going. And so we need to change this notation a little bit. So instead of x1, we're just going to call that x. And if this is x right here, then that means when we plug it into the function, we'll have f of x. So that's our change, x, and then f of x. And then what we're going to say is the distance between x1 and x2, this is distance here, we're going to call that h. That's the distance between those 2 points. And if that's the case, then x2 is x plus h. So here is x. If we go an h distance away, we're now at x plus h. And this x plus h, we will plug into the function. And so instead of y2, we'll have the function at x plus h. And this is our change in notation here then. So let's just plug that in to the slope formula. So we have y2. y2 is now f of x plus h. y1 is now f of x. And x2 minus x1, The distance between these 2 points is h. So I want to stress that this f of x plus h minus f of x all divided by h, I want to stress that this is just the same as rise over run. We haven't changed the meaning of anything. All we're doing is labeling these things differently. We've changed notation. So let's take a look at what we have here. We've got what you've seen from algebra, rise over run, y2 minus y1. And then what I just showed you here is changing that notation. This notation still means the same thing, it's just different notation. And then what we talked about next is if we take this formula for slope for the linear function and then apply it to something that has curvature. If we apply the same function to what has curvature, we then get this secant line. And a secant is, again, a linear function, and this gives us the slope of that secant line. And then what we want to do is we want the run to get forever smaller. And if we do that, then the secant will approach the tangent line. And the tangent is the slope of the function at that point. So to make h get forever smaller, we take the limit. And the slope of the tangent line is the limit of the secant. And this is ultimately called the derivative. So here it is on our graph again. The derivative at a point. The derivative is the slope of the function at this point. Because if you follow the function along, you can see at every point it's got a different slope. So for instance, right at the top here, the slope would be a horizontal line right at the top. If you were standing over here, though, the slope would be sloping down then. And imagine this red line was a hill. And you're walking up this hill. And you're right here at this point. And you ask yourself, I wonder how steep it is right here. That's the derivative. The derivative is telling you how steep this slope is right at where you're standing. And then you might continue to walk up the hill, and then you get to the very top of the hill, and you wonder, I wonder how steep it is here. Well, if you're at the top of the hill, then your slope is just a horizontal line going straight across. Zero slope. And as you walk down your hill, maybe you're over here, you wonder how steep is the hill right here. That's the derivative. The derivative tells you at every point how steep that function is, what its slope is at that point. And the derivative has some notation. And these are both very common notations. So here we just put the apostrophe there. I don't know why this is called prime, but it is. And so we read this as f prime. And there is some other notation. Calculus actually originated with Newton, Isaac Newton, and Leibniz. Newton liked the prime notation, which definitely has its uses. And Leibniz had what I like to call this differential notation, which also means the derivative. So we have these two notations that both mean the derivative, and they both have their uses. And I want to mention something about this df dx, since this is probably the first time you're seeing this. And I want to go back to what you saw in algebra with the y2 minus 1 over x2 minus x1 for rise over run. Is you may have seen this sometimes written as delta y over delta x. And the delta specifically means change. So you would say you would read this as the change in y over the change in x. And change in math, the symbol is always defined as final minus initial. And so that's what we have here, x2 minus x1, final minus initial. Change is always defined that way with this symbol. And in algebra, this change is a finite value. It could be large, it could be small. Either way, it's some finite number here. What happens in a change from algebra to calculus is that this delta y over delta x goes to dy over dx. So this little d here doesn't mean derivative. It actually means delta, this symbol. However, this little d is no longer a finite quantity. This dy now means an infinitesimal quantity. So this dy means an infinitesimal change in y. And let me just say that one more time. If you write, I guess I'll go to the left here. If you just write y down, that's a function. If I would write delta y down, that means the change in y. So y is the function. Delta y would mean the change in y. And if I wrote dy, that would mean the infinitesimal change in y. And that is one of the changes from algebra to calculus is delta y goes to dy. So we're going to work this out on some functions. So let me just bring up here what our definition is here for the derivative. This is the derivative here. And let's check this out then on something you already know the answer to. And that is just a constant function. What is the slope of a constant function? Well, it's a horizontal line, and it has zero slope everywhere. So we're going to use the derivative to get that zero answer. So notice what we have to plug in. We need to plug in the function, and we need to plug in what x plus h is. So let's do that. We have what the function is right here, just 5. And then what is x plus h when we put it into the function? Well, it's a constant function, so no matter what we put in, it's still 5 for a constant function. So let's take this over here and plug stuff in. So we have f of x plus h is 5. We have f of x is also 5. So all I did was plug our stuff in into the limit. Just plugged our information in. And then we can simplify this. because 5 minus 5 is 0. And I think this is a pretty cool limit. What is the limit of 0 over h as h goes to 0? Now remember, the simple thing to do is to plug 0 in and see if it works. But if we plug 0 in, we get 0 over 0, which is the indeterminate form, which means there's something else we can do. And what is that something else we can do? Well, if you think about it, what is 0 divided by 2? What is 0 divided by 10? What is 0 divided by h? It's 0. And this messes with people's brains a little bit sometimes, because how can 0 divided by 0 be 0? I thought that was indeterminate. Well, you have to remember that plugging the number in is the simple thing to do. But underneath the logic there, you have to also remember that h never technically equals 0. So technically, this is always 0 divided by a number. And 0 divided by a number is 0. And the limit of a constant is always that constant. And there's our answer. The slope of this function is 0, which is what we expected for a horizontal line. So let's check out another one. And another one that you will know the answer to, a linear function. What is the slope of this linear function? Well, you can already identify its slope is 2. So how can we get 2 out of the derivative? Well, let's just take the derivative and plug our stuff in. So we have f of x plus h. So we're going to plug x plus h into the function. And let me just do that separately. So we're going to plug x plus h into the function. That then means, and by the way, a good habit here, whenever you substitute, use parentheses is a good habit so that you make sure you distribute correctly. We are going to plug in x plus h. So here's the function, and this is what we get when we plug x plus h into the function. So going back to the derivative, so we have our f of x plus h, which is 2x plus h. And then we subtract off the function, which is 2x. So we subtract that off. And that's all divided by h. Now recall, the simple thing to do is to simply plug the number in and see if it works. And if we plug in h, of course the denominator will be 0. And if we plug in h, the numerator will be 2x minus 2x, which is also 0. In other words, the derivative is always in the indeterminate form. As it stands like this. When you plug your information in, like I just did, this will always be in an indeterminate form. And there's always going to be something more you can do. And what is that? Well, we can just do what we can. So we'll distribute stuff in the numerator and gather like terms. So just distributing there in the numerator. And then the 2x's will subtract out. And then those h's will divide out. And the limit of a constant and there's our 2. The slope you already expected. So let's try another one. One you probably don't know the answer to. X squared. What are the slopes of this function? So if I asked you, what is the slope of this function at 4? Well, you could plug 4 in and tell me the function output is 16. But that doesn't tell me how steep it is right there. That's what the derivative does. So to start, we know we're going to need x plus h. So let's just do that. So we're going to plug x plus h into the function, which then gives us x plus h and all that squared. And then we will take this and plug it into the derivative. So we have first, plug in f of x plus h. Okay? We know that is x plus h squared. And now we have minus the function. So we have minus and then our function. And all of that is divided by h. And again, if you plug in h, you can see this is 0 divided by 0. So there's something more we can do. And let's just do whatever we can. And something we can do is distribute this x plus h2. Or distribute. I was going to say factor there, but we're going to FOIL that out. That's distribution. And so that would give us x squared plus 2hx plus h squared. So I just distributed this out, FOIL. And we'll get that. And why'd we do that? Well, because now we can gather like terms and hope things simplify. And we can see these x squareds will subtract out. And since every term has an h, we can divide one of those h's out. So there we go. So I divided an h out from everything. And now here is our limit. Now again, the simple thing to do is if you can plug in 0 and it works, then that's it. So if you look at this limit, as h gets forever smaller, it's basically just going away. And then this limit is 2x. So this is what we would write. We would say, whoops. We would say, here's our function. And then we'd stick the prime here, and we'd say, this is the derivative. Here's our function, which gives us all the outputs from our inputs. And then the derivative gives us the slope everywhere of our function. So back to my original question. What is the slope at 4? So if you plug in 4, you get 16. That's the function value. But if we plug in 4 into the derivative, we find the slope is 8. So let's say, what is the slope of this function at 10? Well, plug 10 into the derivative. The slope is 20. What about, what's the slope at 0? Well, plug 0 in, we get 0. So let's take a look at that on a graph. So here is x squared, and here is the derivative we just found, 2x. So what is the slope at 0? Well, that's right here. The derivative is giving us the slope of this tangent line. What is the slope at 4? Well, right here is 4. And the derivative is telling us that the slope of the function right here at an input of 4, that slope is 8. And then I asked, where is it at 10? Well, if we go to 10, the slope of the function right here at 10 is 20. So the derivative is giving us the slope at every point on a function. And this slope is also the slope of the tangent line. And your book does call this the instantaneous rate of change. So let's check out another one. How about the square root of x? So now in using our limit here, we also need x plus h in here. So let's just do that. Let's just plug x plus h into the function, and then we get the square root of x plus h. And now that we have that information, we can just plug it into the limit over here. So we have f of x plus h, which we just figured out is the square root of x plus h. And then this is minus the original function, which is just square root of x, and all divided by h. So here is plugging our information into the limit, and then we will do what we can on it. And what should we do when we have square roots? We should multiply by the conjugate. Oops, that's not what I meant to paste in there. And a conjugate means switching this sign. So let's do that. In the numerator, let me just actually write that all out. So in the numerator, we have square root of x plus h times the square root of x plus h, which is x plus h. And we have this square root times this one, and then this times this one, which are the same but the opposite, so they subtract out. That always happens with the conjugate. This is why the conjugate is useful, because those middle terms always subtract out. And then finally we have the outers here. Square root minus square root of x times positive square root of x gets us a minus x. And in the denominator, we are not going to distribute any of that out because we want the h to go away. We ultimately want that to be gone. And so to get rid of that, we do need to keep it as a factor. And so that's our next step there. Here's multiplying by the conjugate. And here is doing that multiplication up, distributing it all out. And now we will simplify. See what we can do. So in the numerator, we have x minus x. So that'll subtract out. And now right here, this is why we didn't distribute, because now h divided by h means these divide out. And so here's our limit we're doing. Here is our limit. And remember, the simple thing to do is just plug in the number. If that works, then it works. So if we just plug in 0, that's what we get. So we plugged in 0, and there's no division by 0, and there's no 0 divided by 0. So we didn't get any of those failures. And here is our limit. And then square root of x plus square root of x can add together to get 2 square root of x. And that's our answer. This is the derivative. And the derivative tells us the slope everywhere of that function. So here is our function. And here is our derivative. And the derivative tells us the slope everywhere of the function. Now notice the derivative has a square root, so it doesn't accept negative values, which should make sense. In other words, the derivative doesn't exist at negative values because the function doesn't exist at negative values. So let's check out another one. The major goal here with 3.2 is to get you to do derivatives through the limit. So we will have 2 more tests to go in detail about the derivative, so we have a lot more to say about it. But the primary goal here for 3.2 is, can you get derivatives using the limit? Let's try one more example. How about 3 over x? And over here is our derivative. And we need x plus h. So let's do that. And we'll plug that into the function, which means we have 3 over x plus h. And then we will take this information and plug it into the limit. So just always trying to show you the limit over here and what we're plugging in. So we're going to plug in f of x plus h, which we figured out is 3 over x plus h. And we're subtracting off the original function. The original function is 3 over x. And all that is divided by h. And so there is plugging all our information into the limit. Now, if you recall back to section 2.2, you might be noticing that, wow, these are limits we already did in section 2.2. But instead of those being practice problems, they now have a purpose. These limits are getting us the derivative. So if you recall how to do this type of limit, is we added the numerator together with a common denominator. So in the numerator here, the common denominator is x times x plus h. Which means we multiply this factor by x. And on the right here, we multiply this factor by, these are terms. We multiply this term by x plus h. So we'll have minus 3 times x plus h. So just adding those together with a common denominator. Getting pretty messy looking. So let me rewrite this mess. Instead of division by h, we can always write that as multiplication by a reciprocal. So it makes it look a little bit nicer doing that. And we will distribute in the numerator here and gather like terms. So minus 3 times x is minus 3x. And minus 3 times h is minus 3h. And then these 3x's subtract out. And what else can we do? Well, these h's divide out. And there's our limit. There's nothing more to simplify. And notice right here, if you plug in h, you get 0 over 0. So this is still in the indeterminate form. But once the h's divide out, notice on the right, we are no longer in the indeterminate form, which means we now have our answer. So as h goes to 0, this is slowly going away, and all we have left in is x times x. And that's our derivative. So here was our function. And here is our derivative. And again, this derivative, this function here, the derivative, gives us the slope at every point of the original function. And notice again, the original function has division by 0. So the function doesn't exist at 0, because it's going to infinity. And notice that's also true with the derivative. There is no derivative at 0, because the function doesn't exist there. So there's always a nice consistency between the derivative and the function. And we will talk much more about the more detailed aspects of this relationship. But for now, the only goal here for this homework and the test is to get this derivative by using the definition of the limit. That's the goal here and what will be expected of you. I'm going to give you a function. Can you tell me the derivative? And in closing here, I do have to say, for test 1, if you know how to get the derivative through patterns, that won't be acceptable for test 1. If you don't know what I'm talking about, don't worry. You have nothing to worry about. If you don't know what I'm talking about, you'll know what I'm talking about next week. But for anybody who's taken 221 before or knows something about the derivative, no patterns will be accepted for test 1. Everybody will be treated the same, that you all have to get the derivative by using the limit. So I just want to make that clear, because that's always an issue with test 1 here for people who have taken a calculus class before. No patterns will be accepted for test 1. You have to use the limit. And if you don't know what that means, you have nothing to worry about, but you will learn what that means next week.